Any questions from yesterday's discussion? All right, well, let's do this. That's what we got to at the end. Step 1 is an activation of the electrophile. So we have bromine to exist as the diatomic element. And then I'm gonna be all cheesy like this and not do the Lewis structure. So how many bonds does a halogen like to have normally? No. Yeah, 1. So what's the formal charge on this bromine atom? It's going to have a plus charge. Then we have an attack of the electrophile. So of course there's hydrogens. So right now we have this carbon that only has 3 bonds, and so it's positively charged. And then of course if we wanted to, nobody wants to, but here's our resonance structures. You can draw those electrons moving over there, gives you that one. Draw these moving down, puts the charge there. Next up, loss of a proton. So I'm going to just go to my first resonance structure. And so right up here, we have some FeBr4 with a minus charge. So FeBr4 minus charge grabs that proton. Those jump down. And we can think of it as being the one dangling bromide on the end that has the negative charge. So there's our HBr. And we've regenerated our catalyst. Any questions on this mechanism? Good. Everything's working. Yesterday was a disaster. Nothing worked. Well, with the intro to chem class.
If you had excess, since you regenerate your catalyst, would it continue to brominate the other double bonds, or like?
That's going to come up a little bit later. For right now, let's just pretend we use a stoichiometric amount, and that's not an issue. All right, so here's what we just went over. So this is forming the cation. That's generally always the rate. I should have lost a half point on my mechanism. I did not write. Rate limiting step, that's the rate limiting step. And this transition state is when this comes by and pulls that proton off and those electrons jump down. So chlorination, same type of setup. We have a catalyst, use chlorine. Probably harder to do on the bench top because this is a gas. So this is probably only done industrially. And we could use ferric chloride, but aluminum chloride's a little cheaper, and that's generally what is used. And we can put iodine on a benzene ring. So there's a reaction with the nitric acid, which is a powerful oxidizing agent actually. And we use that to produce a iodide cation. Maybe I should have said iodine, because I always tell people ends in "ide," it's probably negative charged, like cyanide, hydroxide, all the rest of those. So here's how that works. You're in an acidic solution. There's our nitric acid. There's our elemental iodine. And notice, so we get some NO2. And then this is the electrophile, attacks the double bonds, get the sigma complex, and we can nitrate a benzene ring. So there's a reaction between these two, makes an electrophile. We'll see here in a second. Sulfuric acid acts as a catalyst, allowing the reaction to be faster and at lower temperatures. We get nitrobenzene, pretty good yield, 85%. So this nitronium cation, NO2 with a plus charge, that is the electrophile. So here's our two acids in all their glory with Lewis structures, and we pull a proton off of the sulfuric acid. So now we have this protonated nitric acid, and you've learned that water's a good leaving group, and when that leaves, you get this nitronium ion. Maybe it's counterbalanced by the negative charge there, so charge is being conserved, but this nitronium ion is the business end of nitration of benzene. So all these reactions have very similar mechanism. You generate an electrophile, the electrophile attacks the benzene ring, you get a carbocation, and we're going to look over the next few days quite a bit about what's going on with some of the sigma complex thing. Probably at the end of today's lecture you'll get a taste for that. So sulfuric acid was the catalyst. So here's a hydrogen sulfate, pulls that proton off, those electrons jump down, and now we have nitro benzene, and we've regenerated our catalyst. So interesting thing here, nitrobenzene, we just write the benzene ring in NO2, there's no charge, but look, it must be some resonance hybrid. So we have a formal charge of +1 on nitrogen and a formal charge of -1 on that oxygen. But this plus charge is going to come back and dictate things if we start with nitrobenzene. So we're going to put more than one substituent on a benzene ring. That was very ugly. So once we get a nitro group on a benzene ring, we can use these metals in the presence of acid and reduce this. If there was just a hydrogen here, we'd call this aniline or analide. So we can reduce a nitro group to an amino group. And this is the best method for adding an amino group. You can't do it directly. You got to nitrate it and then reduce the nitro group. Sulfonation of benzene. So here's a sulfur trioxide. That's the electrophile. Have you ever got so mad that smoke comes out your ears? Somebody says you're fuming. Where'd that come from? Well, probably Latin. Yo fumo would be I smoke, but how do you get SO3 in H2SO4? If you just take H2SO4 and put it in a flask and start heating it, pretty soon you'll see white smoke and you've created some SO3 inside there. And so you get some fuming sulfuric acid, and it has the sulfur trioxide in it. The SO3H group is called sulfonic acid, and this might remind you of tosylate chemistry, those tosylates in the alcohol chapter. We had the methyl sulfonic, paramethyl benzosulfonic acid was the way we made tosylates out of alcohols. So we draw SO3 with no charge housed in an electrophile. So we have 3 sulfide bonds drawing electron density away from the sulfur atom. These 3 oxygens draw electron density away from that. So that is the business end here. Those electrons see that positive charge. We get a sigma complex, and then hydrogen sulfate pulls a proton off, regenerate the double bond, and there's our benzene sulfonate anion. Loss of the proton on the tetrahedral carbon and reprotonation of oxygen gives benzyl sulfonic acid once we put one more proton on there. Interesting thing would be the hydrolysis or the desulfonation reaction. Here's our benzosulfonic acid, add some water, heat this thing up, and we get benzene and H2SO4. So somewhat reversible. So we can put a sulfonic acid group on a benzene ring and then remove it later if need be for some reason. So what is the mechanism? Double bonds grab a proton, and you can have the electrons in this bond jumping down, and notice you get your SO3, but SO3 and water go back to H2SO4. In the desulfonation reaction, a proton adds to the ring as the electrophile, and loss of sulfur trioxide gives back benzene. And so let me just talk about Le Chatelier's principle here. When we wanted to form this, we used fuming sulfuric acid. And sulfuric acid really wants to soak up water. So when we go this way, it's very anhydrous. And so this way, going the other way, you just use a very dilute aqueous acid solution, so you got a lot of water. So a large excess of one reactant is going to try and push things in the forward direction. So after all those sigma complexes, we don't want you to get bored. So now we have a substituent on our benzene ring, and we go ahead and nitrate it. So here's our nitrating agent. And what do we notice that's interesting? Or maybe we say it's horrible. We got a mixture of products. And mixtures are expensive to separate. Well, what's interesting is we get ortho and para predominate, and the meta we get hardly any, 4%. And so the question is, why is this? Must be something going on in the sigma complex. Oh, there's other interesting things. Toluene reacts 25 times faster than benzene. So an alkyl group must activate things for electrophilic aromatic substitution. And so to answer Jonathan's question earlier about the second bromination, halides are somewhat deactivators. So once you put one on, it's going to be a little less reactive. Now you can still do some reactions, and what we're going to learn is ortho para directors and meta directors. The product contains a mixture mostly ortho para. Why is that? So ortho is right next to the substituent, para is directly across the ring, and so we have these electrons grab the nitronium ion, and straight up we form a tertiary carbocation. And then here's the resonance structures. Let's put it in the tertiary position. Well, we get a secondary right at the beginning, but as these things move around, there's a tertiary. And which did we have more of, the ortho or the para? I think we had more of the para. We can just back up and look. I mean, more of the ortho, I'm sorry, I misspoke. A little more ortho than para. A little more ortho than para. Maybe nature knows. If it strikes here, it goes right to the tertiary. If it strikes right here, it can get a tertiary. What about the meta position? I think we're going to look at the meta after this. All right, so take-home knowledge would be alkyl groups activate a benzene ring. So here's benzene, and notice here's this would be like toluene, and here we see toluene reacting, giving these products. Both of them have the tertiary cation. If it reacts to give the meta, there's a secondary. There's probably a little more of the picture. I ought to change the order of these slides. So let's put it in the meta position. There's a secondary carbocation, secondary. So if the nitronium goes to the meta position, you never get a tertiary carbocation in the sigma complex, and nature knows that, and that is why you have a higher energy barrier to get over. That's why we only got 4% instead of the 60-40 that we got with the ortho para. So when substitution occurs at the meta position, we never get to delocalize the positive charge onto a tertiary carbon. But those other two positions for the electrophile to hit, we do get that to occur. So let's move from toluene to ethyl benzene. Probably makes no difference. And let's brominate it. And now we see that we still get ortho and para, only for some reason we tend to get more of the para over the bromo. But we say that alkyl groups are activating substituents and that they direct to the ortho and para positions on the benzene ring. And this is an inductive effect because the alkyl groups can donate electron density to the ring through the sigma bond, making them more active. Any questions?